So this is 2018 Physics C, question number 2. So I'm just going to look at this, and so far I know this is going to be a momentum problem because we have two things colliding, probably some energy because we've got a spring there. Oh, we got a graph, a force versus time graph. Area is impulse. Boom. So that's what I have. Now let's actually read it. Two carts, no friction, sensor exerted. Okay. Cart 1 has an initial speed of 3, shown it's at rest. All this is 0.5 kilograms, that's 1.05 kilograms. Spring doesn't have mass. Spring constant, and there we go. Assume models the data. Okay, so this is the, okay, using integral calculus, calculate the total impulse received by the cart during the collision. So they gave us the equation, and so therefore we're going to use the equation. So 2a, we know that impulse, delta p, is the integral of f dt, and so it looks like we have to figure out what the bounds are. It's from 0 to 0.16 seconds, it looks like. And so let's just plug that in. 3200 newtons per second squared, t squared minus 500 newtons per second, t dt from 0 to 0.16. Boom. Okay, cool. That becomes t cubed divided by 3. And so that's going to be 1067 roughly, minus 250 t squared between 0 and 0.16. Already plugged in units there. Notice I have nothing there. And so now we're just going to plug in 1067 0.16 cubed minus 250 0.16 squared. Minus, and all these terms zero out. So I'm going to throw that into the calculator, 0.16, 0.16 cubed, great, times 1067. I'm just going to jot that down. What that number is, 4.37, okay, minus 250 times 0.16 times 0.16. 6.4. Oh good, the answer is negative. You should be thinking about why the answer should be negative. 2.03 Newton seconds. Look at this, that area, folks, is a negative area, and therefore it should definitely be a negative impulse. Awesome. Next, calculate the speed of the cart of 1 after the collision. Okay, so that's the impulse it receives, and so 2b delta p is equal to m delta v, since the m is not changing, and so that's going to be 0.5 kg. V final is what I'm looking for. This is negative 2.03 Newton seconds minus 3 meters per second. So negative 2.03 is equal to 0.5 VF minus 1.5. Let's put that over to the other side and get that done. So 1.3 minus 1.5, okay, divided by 0.5, and that gives us negative 0.106 meters per second. There we go. So next, in which direction does the cart move after the collision? Well, that's pretty clear. I got a negative sign there. They've already imposed a positive to the right, so it is to the left. There we go. C, calculate the speed of cart 2 after the collision. Okay, so nice and simple there. We're just going to go Pi cis is equal to Pf cis because the net external force is equal to 0. So the initial momentum of the system is just the mass of object 1, 0.5 kilograms, times its initial momentum, is equal to, there's a quicker way to do this, by the way, but let's just do it this way. I got 0.5 kg times negative 1.06 meters per second plus, and what's that thing, 1.05 kg VF2, and so we can just move all this around. I know that when I move that over there, that this becomes 2.03 is equal to 1.05 VF2, so 2.03 divided by 1.05, is it 1.05? Yeah, okay, Great. And so then VF is equal to 1.99 meters per second VF2, right? I should have realized that the delta P of 1 is going to equal to negative delta P of 2 because the momentum is conserved. The loss in one object's momentum is the gain in the other. That would have been a shortcut, but here we go. Show that the collision between the two is elastic. Great. So if I want to show that it's elastic, what I have to show is that energy is conserved. Great. So show that energy is conserved. We'd say kinetic energy initially is 1/2 m1v1 initial squared. So that's 1/2 0.5 kilograms times 3 meters per second quantity squared. And that gives us, what is that, 9/2 of 9, 4.2.25 joules. Okay, KE final of 1 plus KE final of 2, so that's 1/2 0.5 kg. And we said negative, actually we're just putting in speeds here, so 1.06 meters per second squared plus 1/2 1.05 kg, and then this is 1.99 meters per second. And if we do those numbers, let's see what we get. Okay, times 0.05, I'm just gonna plus 2.079, 1.06 squared, 4, and I'm getting this is 0.28. Oh, actually I'm getting a little bit of an overage there, because we should get that the addition of those two is that. Let's see if I made a math error earlier in this extravaganza. Boom. 3, 5. Okay. No, it doesn't look like I have made a math error anywhere. Oh, there it is. Okay. Sorry, folks. Coming back here, this should have been 1.93. All right. So then this is 1.93, and let me put that back in. Squared times 0.5 times 1.05. That's the nice thing about this, knowing what the result is supposed to be. Okay. And oh yeah, look, that works. That's round about 2.25 there for elastic, because energy initial is equal to energy final. Done. Okay, D, calculate the speed of the center of mass of the two-car system. So the COM is equal to the sum of the MVs over the sum of the Ms. So that's going to be 0.5 kilograms times 3 meters per second all over, well, plus 0, that term 0, 0.5 kilograms plus 1.05 kilograms, and that gives us 1.5 divided by 1.55, okay, 0.968 meters per second. So that is the velocity of the center of mass of the system. Now, remember, we also know that the velocity of the center of mass of the system has to be constant through a collision as long as momentum is conserved, that the preservation of the center of mass motion is the same thing as the conservation of momentum right there. Sum of the MVs is constant. That's the sum of the momenta is constant. And so the second part of this, to calculate the maximum potential energy, well, we already know the energy of the system is that, right? And so energy initial has to be equal to the energy during this thing, because the work non-conservative is equal to 0. So this is 2.25 joules. Now remember, this is the velocity of the center of mass. It is also what the velocity would be if the two objects stuck together in an inelastic collision, right? Because this would be like the combined mass. Remember that the max potential energy here is going to occur when this spring has been maximally compressed. That's when the relative velocity between these two objects has reached 0, and we treat it instantaneously like we do in inelastic collision. That's sort of the trick of this problem, is being able to know those things. So I don't think this year's AP is going to be asking you to do all this calculations, but think about all the little physics hints and what do I expect and why do I expect it, things that I've been talking about. They could ask you narrative pieces about all those things. Anyway, let's just do this. So this has got to be equal to the kinetic energy of the combined term when it's traveling at that speed, 0.968 meters per second squared. And it says that maximum potential energy, I actually don't need to know what K is. That was a sucker's move there. I just need to know what that potential energy is. So I'm just going to take 1.55 divided by 2 times 0.968 squared. And find out that this is 0.73 joules plus U sub S 2.25 G is equal to that. So just subtract that off, and then we've got it. So the maximum potential energy is going to occur at 1.5, not occur at, but will be 1.52 joules. And there you go. That is our problem. Whew. A lot of stuff going on in that problem, but it was really good to talk about a different type of graph, what they could ask. I'm actually surprised that they didn't make us estimate this by counting boxes rather than just giving us the function, because knowing an integration is the same thing as an area, I think is an important calculus thing that they could ask you about. But here, mostly about conservation of momentum with conservation of energy and understanding about what's going on during that elastic collision.